iSQL, and this is my project partner Joshua Bradfield. And today we're here to talk about our final year project, this 3D control of a laser micromachining system. So what is laser micromachining? It's basically machine on material in micron scale. So the final product will be very tiny, such as microfluid devices, such as waveguides, microlens arrays, or photolithography masks. So how we do this, there will be two techniques. One is ablation, which is essentially removal of material. By striking a laser onto the material will heat up and transform into plasma and then burst off. And the second technique is subablation, which is transfer the material property, alter the material properties such as refractive index, such as the chemical resistivity. And then there will be two lasers that we'll be using. One is the UV laser, the other is infrared laser. They have very different wavelength and energy, which allows us to use on different materials. But they have both pulse lasers rather than continuous. So how this works is that the two lasers will go through a set of attenuators, which controls the power. And then we'll go through a set of masks, which change the beam, change the size of the beam, shape of the beam as well. And then it will go through a series of alignment tubes and objective lenses, then finally focused onto the parts. And the parts will be attached to the stage, like shown here. This is our actual stage that we'll be machined on. And this is the actual stage. It is controlled by this glow motion controller, which is an 8-axis interpolator. And we'll be using 6 of these 8 axes, which is the normal X, Y, Z axis, the rotational theta axis, the laser axis, and also the attenuator, which we also treat it as an axis. And there's an existing software which is produced by the JPSA company. At the moment, it only allows them to do 2D drawings, which is lines and arcs, although the arcs don't usually work. And when people have to print surfaces, they have to manually put in the lines for the laser path to go, which is not really convenient. So our main goal for this project is to develop this new rapid prototyping system that allows both 2D and 3D prototyping. So we're able to take in all those popular formats of this CAD file. And it has to be very simple to use for all kind of user. And the overall system architecture has to be simple as well for future developers to extend on our project. So our main goal is this 3D. It's very useful in terms of producing some fine devices like this Eiffel Tower and some useful ones like gears for MEM devices. And it should be able to do direct write, single process, and without the need for masks. So we're using C# as our environment because it's simple, and there will be 2 programs in our overall software. One is CAD to Laser Wizard, and the other one is basically control of the stage and alignment. So there's a series of hardware that we'll be controlling, and it is controlled by these 2 controllers, the glow motion controller I talked about earlier and the other star controller. And then everything is wrapped up in this background code module, finally connect to the user interface. But really what we're interested in is this part here, the interpolator part, which takes in the CAD file and use the Caterpillar library that we had and then display it, and then how we transfer it to the laser where we can produce on the laser. Okay, now I'll hand it over to Josh to talk to you more about our system.
Thank you, Isaac. Just before I talk about the interpolation, I'm just going to go back and cover some more about laser micromachining. Isaac mentioned that we're using pulse lasers. This is really important because we're not using a continuous laser beam. We're not firing a continuous laser beam down into a surface and exposing it for a period of time. Instead, we're firing discrete packets of energy. We know the quantity of energy. And we're focusing these down to a specific volume. And given that we know the material properties, we can effect a desired change at a specific location. So whether that's removing a set amount of material from a surface, or whether that's changing material properties at a set volume. We know what that is, and we're placing it where we want it. And the idea is to stitch these together to create exposed regions We can build that up as either a surface or as a solid. And so our prime objective, which was there before, was to take a CAD file and to produce these exposed regions. And one of the ways we do this is we have 2D and 3D paths. On our system, we're restricted to straight line segments, so everything we interpolate is going to be in straight lines. And the way we do this is obviously dependent on your desired accuracy. You take your arbitrary geometry and you're going to convert that into a set of straight lines, and obviously if you do it more accurately, it's going to approximate your end product. Our minimum accuracy is 100 nanometers. That's the kind of scale we're working on. And we'll be able to do points, lines, arcs, ellipses, and splines, which gives us a really good cover of geometry. And the idea is that the laser will follow that path, and that path determines the exposed region, whether that's a material change, material removal, or like a change in chemical resistivity. One of the other things we want to be able to do is take a 2D surface and hatch it according to a set of criteria. So depending on how much material you want to remove, for instance. In the past, you've had to draw these lines manually, and you'd have to change it manually if you want to change your machining settings. We want to do that automatically in a variety of different ways. We're also going to be able to do curve profiles, although I haven't shown that there, so that's very useful. And then we'll take those profiles and interpolate them into our straight line segments like we did before. Now, obviously, we want to do 3D. We're going to do that in one of two ways. The first is intensity modulated machining. Basically, what happens is you take a focal volume that's stationary in the z-axis. In other words, we don't change the focal point of the z of the laser. We only move it in the x and the y-axis. We take our solid object and we slice it to get a series of distances in the z-axis, which we use to construct an exposure map. Here. The focal volume has to have a high aspect ratio for us to do this. We want it to be log in relation to the size of your part. And we want the relationship between the exposure to the laser and the amount of material removed to be kind of clearly defined. So if I fire one shot, I remove 1 micron of material. If I fire 10 shots, I remove 10 microns of material. And here in this exposure map, you can see where it's darker. That's where I want to remove more material. So we end up building a 3D structure. So you can see then that we can only build 3D structures that we can see from the surface, from the machining angle. If we want to build a more complicated structure, like for instance an hourglass shape, we're going to have to do something different. And that approach is a layered machining approach. And the idea is kind of completely different. We have a tight focus as opposed to this large focus. And we move the laser's focal volume in the z-axis as well. We start at the bottom, and we do a layer, and then we move our way up. And the idea is to change the property of the material so that it can be preferentially etched. And so what we do is we take our 3D structure. Again, we slice it, but this time horizontally, to produce a series of surfaces, which we then hatch using our hatching algorithm we talked about before. And then this all boils down to getting this to the stage. And this is where we produce a motion profile. So we take our linear segments and we interpolate them with firing the laser, and we kind of coordinate the stage motion and the laser together. And we have to be really strict about our kinematics according to different system constraints, like the maximum axis acceleration, maximum velocity that an axis can handle. Each axis in our system has a different constraint. So we have to take that into consideration when we write our algorithm. Also, we have to take into desired quality. Sometimes overshoot is acceptable, sometimes it's not. And it's going to really affect the time it takes to machine something. And so that's important and needs to be a variable. We're going to use a look-ahead buffer. The idea is that you take a point and you process it, and you keep on doing this, keep on adding your points. So you take a linear segment and you add it to this buffer, and then you update the motion profile. The advantage of doing this is that you can do it in a real-time process where you send your points to the machining stage as you're processing these linear segments, which is really cool. Often because we have large drawings, lots of amounts of data, and we need to be able to process that quickly. So in terms of future work, apart from these algorithms that we've described, we're going to have a really optimum user interface because one of our main goals is having a rapid prototype system, so it needs to be easy to use. Things like machining wizards, having a materials database that suggests the best settings to use given the material that you're using. Plug-in functionality and macro functionality mean that more experienced users can add their own interfaces to the system so they can do whatever's physically possible with the system. That's our goal. So yeah, I hope that helps you understand our project. Thank you very much.